Hello and welcome to Principles of Mathematics lesson number 24. This will be the last lesson in the first term of the Principles of Mathematics course. The videos after this will be for the next class. So in this video, we're going to discuss real numbers. We've already talked about real numbers and the real number line. We're also going to look at operations on real numbers. We'll discuss the nth root and in particular the square root of a real number, how the expressions a to the 1 over n and a to the n over m can be defined in fact as radicals, and expressions involving radicals and radical exponents are what we will pretty much close with. Now, in a previous video, we've already discussed the fact that every rational number can be expressed as either a terminating decimal or a repeating decimal. It was the ancient Greeks who discovered there are numbers that are neither terminating nor repeating. So we call them non-terminating and non-repeating. We don't need a hyphen for these words. They're actual words in mathematics. Such numbers we've already discussed are referred to as irrational numbers. So as some of the characteristics of irrational numbers are that there must be an infinite number of non-zero digits to the right of the decimal point, and there cannot be a repeating block of digits, because if that turns out to be, then the number would be rational, wouldn't it? Irrational numbers occur in the study of area, for example. The area of a square is calculated using the formula a equals s squared, where s is the length of one of the sides of the square. Of course, we know that all the sides of a square are the same sides. So, for example, if s is 11, we get the area is 11 squared, or 121. On the other hand, if we know the area of a square, then we can calculate the length of each side because we use this formula, a equals s squared. For example, if they tell us that the area of a square is 49, we know that s squared must be 49, so we think to ourselves, what number can I square to get 49? We know that there are actually two numbers. You can square 7 to get 49, or you can square negative 7 to get 49, because negative 7 squared, the negative squared becomes positive. It's like saying negative 1 times 7 squared, right? So it's negative 1 squared times 7 squared, so it's 1 times 49, which is 49. So there are two numbers whose square gives us 49. But since we're dealing with a real object, the length of a side of a square can't be negative, so we reject the negative result and we only take the positive one. So the length of a side of a square whose area is 49 would be 7. The square root of a non-negative number a is a number x such that x squared equals a. So, for example, we talked about the number 49 in the previous slide, right? So the square roots of 49 would be any real number that we can square to get 49. So we just saw that there are two. There is 7, because 7 squared is 49, and there is negative 7, because quantity negative 7 squared is also 49. Now, however, of the two of them, the positive one we give a special name to. We say it's called the principal square root of a, and it's the non-negative, in this case positive, but in general the non-negative number, such that when you square it you get a. All right, what if we want to find the square roots of 144? So we're looking for numbers that when we square we get 144. So of course we know there are two of them, right? 12 and negative 12. But what if they only wanted the principal square root of 144? Remember, in that case there's only one, and that's the non-negative one, 12. Now here, when they say find the square root of 4 over 9 with this notation, this is the principal square root, because if we wanted the negative square root of 4/9, we would have just put a negative sign next to it. So there is no ambiguity here. This is going to be 2/3. Why? Because think about it. What happens when you square 2/3? You get 2 squared, which is 4, over 3 squared, which is 9. So there is the principal square root of 4/9. We can take the notion of the square root of a number even further and talk about the nth root of a number, like the nth root of x. The nth root of x is basically the number that you would have to raise to the power of n to get x. For example, the cube root of 27 would be whatever number it is that you would have to cube to get 27. If you think about it, that's going to have to be 3, right? Because 3 cubed is 27. So we get the cube root of 27 equals 3. What about the cube root of, say, 64? Is there a number that you can think of when you cube, you get 64? Yes, in fact, that is 4. So the cube root of 64 is 4. Why? Because 4 cubed equals 64. Now, we don't have the same ambiguity with cube roots that we do with square roots. We don't get 2 cube roots, we just get 1 cube root, right? With the even powers, we always have that situation where we may have 2 results, but not with, with even indices, not powers, I meant. So when you have the nth root of x, the expression itself is called the radical. We call n the index of the radical. We call x, which is the number under the radical, the radicand. All right. Now, notice that if n is even and x is positive, then the principal nth root is going to be positive, right? For example, the 4th root of 16 will be 2, right? Now, if n is even and the number under the radical, the radicand, is negative, then the nth root is not going to be a real number, because think about it. If I look at the 4th root of negative 16, what am I looking for? I'm looking for some number that when I raise to the power of 4, I get negative 16. But that's impossible, because when I take any negative number or positive number and raise it to the power of 4, my answer is always going to be non-negative, right? In most cases positive, with the exception of 0, right? So therefore, there is no such number. Well, no such real number, right? It works with square root too. But what is the square root of negative 4? Well, I don't know of a real number that I can square and get a negative 4, because when I square it, I'm not going to end up with a negative number. I'll get 0 or higher, right? All right, so now if n is odd and x is negative, then the nth root of x is negative. So for example, if you take the cube root of negative 27, that's well defined. Remember, odd indices don't create the same problem as even ones. This is well defined and it's just negative 3. Why? Because think about it. What's negative 3 cubed? That's negative 27. Same goes, for example, with the 5th root of negative 32, right? That's just going to be negative 2. Why? Because if you take negative 2, raise it to the power of 5, you get negative 32. Now, if n is odd and x is negative, then, okay, we already described that. Now, this other fact will help us get rid of the situation where the square expression may be under the radical. So we want to avoid this. Normally, most people think that if you see the square root of a squared, well, you're saying what number do you square to get a squared. Isn't it just a? Well, think about it. Negative a, if squared, gives a squared as well. So to deal with that, so that the principal square root always turns out to be non-negative, we say the square root of a squared is the absolute value of a. So now, if we see an expression like, let's see, let me go to a new page so it doesn't get too crowded here. Okay, so when I see, for example, the square root of -4 squared, I know that according to this rule, which says the square root of a squared is the absolute value of a, that's going to be the absolute value of -4, which is 4. Now, notice that you could also say, okay, that's the square root of, what's quantity -4 squared? That's 16, right? And of course, the principal square root of 16 is 4. So no ambiguity there. Now, the square roots of some numbers are rational. For example, let's take the square root of 4. Well, that's just 2, which of course is a rational number because it's in fact a whole number, a natural number, an integer, and we can write a 1 under it, so therefore it's rational, right? But the square root of numbers like square root of 2, they are irrational. Now, in fact, it can be shown that the square root of any non-perfect square whole number is going to be irrational. Now, this gives us a way to generate as many irrational numbers as we like, because here's what we can do is just start with whole numbers, and any one of them that's not a perfect square is going to give me an irrational number. So 2 is not a perfect square, so the square root of 2 is irrational. 3 is not a perfect square, so the square root of 3 is irrational. 5 is not a perfect square, so the square root of 5 is irrational, etc. Notice we've skipped square root of 4 because, again, square root of 4 is rational. How about the square root of 9/16? Where would that fall? Is that rational or irrational? Well, think about it. It can be written as 3/4 because 9/16 is the perfect square of a rational number. So therefore, that would be a rational example of a square root. So remember, just because you have a square root, it doesn't mean you're automatically going to have an irrational number. The requirement is that the radicand has to be non-perfect square. It should not be a perfect square of a whole number or a rational number. One nice graphic description of where square root of 2 popped up, first of all, in geometry with the Greeks was this triangle right here. Notice that this triangle is a right triangle, and it has 2 legs, each of which are length 1. So if we recall the Pythagorean theorem, right? It says the length of one leg squared plus the length of the second leg squared is going to be the length of the hypotenuse squared. The hypotenuse is the longest side of a right triangle, which is opposite the right angle, right? So notice with this, I'm going to get 1 squared plus 1 squared equals x squared. So 1 plus that 1 squared is just 1, the other 1 squared is just 1, so I get 1 plus 1, which is 2, equals x squared. And this is where the original problem came in that made people realize, oh, there are going to be some numbers that are going to be square roots which end up not being rational. All right, so now we know that the number that we have to square to get 2 is the square root of 2, right? So here we get x equals square root of 2. Even though we know that negative square root of 2 squared is also 2, we do not take it for this length of x because, again, it's the length of a physical object, so it has to be non-negative. Well, because it's length, in fact, in this case, obviously it has to be positive. So that's where we get for x being square root of 2. Now, as far as approximating or estimating a square root, Now we know it should fall somewhere between 1 and 2, right? So the question is, can we kind of like get a better estimate for it? Well, the thing is, if you notice on a calculator, for instance, if you calculate 1.4 squared, oh, that was not what I wanted. Let's try it again. So 1.4 squared, we get 1.96. But if we go to 1.5 squared, we get 2.25. So we know it's going to be somewhere between 1.4 and 1.5, right? So that's how we can kind of get a approximate value for a square root. All right, now that we've discussed both rational and irrational numbers, we can remember from a previous video that the set of real numbers R is the union of the set of rational numbers and the set of irrational numbers. In symbolic terms, we write R equals the set of rationals, which we use Q for, union the set of irrationals, which we usually use P for. The decimal form of any real number is either terminating, repeating, or non-repeating. Every integer is a rational number as well as a real number. We know that every rational number is a real number, but not every real number is rational, because as we know, some real numbers are irrational now that we understand things better. So to summarize, I did this in a more graphic way for you in a previous video. Here's a more notational representation. The set of irrationals, remember, all x such that x is a real number to begin with, and it's a decimal that is neither repeats nor terminates, whereas the set of rationals can be shown in two ways. One is the classic way, all x such that x is a fraction where the numerator and denominator are integers and the denominator is not zero. Or we can say all x such that x is a repeating or terminating decimal. And of course, a subset of the set of rational numbers is the set of integers, and a subset of that is the set of whole numbers, and a subset of that the set of natural numbers. We showed this symbolically in this way. The set of natural numbers is a proper subset of the set of whole numbers, which is itself a proper subset of the set of integers. I use Z, they use I in the book. Doesn't matter, they're both okay. The set of integers is a set of a proper subset of the set of rational numbers, and that itself is a subset of the set of real numbers. On this side, we have the lonely group of irrational numbers, which can only be related to the set of real numbers. They have no connection to these other sets. Now, we've already discussed the properties of closure, commutative, and associative for whole numbers, integers, rational numbers. They also work, of course, with real numbers. For real numbers, a and b, a plus b, and ab are both going to be unique real numbers. The commutative properties for addition and multiplication both work for real numbers and hold, and so does the associative property for both addition and multiplication for real numbers. We also have the identity properties for addition, which says 0 is the additive identity, and when added to any real number, it's just going to give you the real number itself. And the multiplicative property, as far as the multiplicative identity, that's 1, because if you multiply it by any real number, you get the real number itself, whether you multiply on the left or right. We also have the familiar inverse properties for addition. Take any number, add it to its opposite, you're going to get to 0, or the other way around, makes no difference. And then we have it for multiplication as well. Take any non-zero real number a, then 1 over a is going to be the multiplicative inverse. And the way it works is that if you take any number and multiply it by its multiplicative inverse or reciprocal, you end up with the number 1. Okay, so remember that. Of course, the additive inverse is also called the opposite, and the multiplicative inverse is also called the reciprocal. We also have the distributive properties, which we have seen before for both addition and subtraction, and they also work for real numbers as well. And the multiplication property of 0, any number times 0 gives 0, and the denseness property for real numbers a and b, there exists a real number c such that c is between a and b. So given any two real numbers, no matter how close they are to each other, right, you're always going to be able to get another real number in between. This is why we say the set of real numbers is very dense. Now, we've already shown you how that works in a previous video. There's no need to repeat that. All right, here we find a very surprising and useful property, and that is the fact that x to the power of 1 over n is none other than the nth root of x. Now, if we think about that, it makes sense. On the one side, we have x to the 1 over n, and on the other side, we have the nth root of x. Now, think about it this way. If I take the x to the power of 1 over n, and I raise it to the power of n, what do I get? Well, I get x, don't I? Because by the power rule, I have to multiply n by 1 over n. What is n times 1 over n? That is just 1, right? So I get x to the 1, which is just x. But I also know from my understanding of what the nth root is, that if I take the nth root of a number and raise it to the power of n, I should get x as well. Like, take the cube root of 8 and cube it. What's the cube root of 8? That's 2. What's 2 cubed? That's 8. So that always works. If you take the nth root of a number and raise it to the power of n, you're going to get the number itself. Now, we can see, because this happens, that these two must be the same thing. And there it is. Now, this other property just follows from that property. Let me quickly demonstrate it for you. So if I have x to the m over n, notice that that's just x to the m to the power of 1 over n, right? So according to this rule, I can just say it's equal to the nth root of x to the m, okay? Now, one other thing that this is equal to, this expression, which is actually very helpful, is this. I can also take x to the m over n and think of it this way, that this is x to the 1 over n to the power of m. This is just playing with the power rule, right? Doesn't matter if the m is here or out there, right? They're both going to multiply to give you m over n. So this means that's the nth root of x to the power of m. So what do these two lines indicate? That these two expressions must be the same either, also. So let me erase this real quickly. So what that indicates is that the nth root of x to the m is the same as taking the nth root first and then raising that to the power of n. So you may think, why is that so important? Because let's say I have the cube root of 64 squared. Now, if I don't have to sit there and figure out what 64 squared is, that would be great, right? Well, because of this rule, I realize I don't have to, because I realize I can just as easily take the cube root of 64 first and then square it. Now, cube root of 64 is easy because I know 4 cubed gives me 64, right? So this is just 4 squared, which gives me 16. So this is a handy rule to remember. To take the nth root of a power, what you can do is take the nth root first and then raise it to the power. All right, for our last example, let's go ahead and see if we can figure out what each of these expressions are. So notice here, with the first one, we have 16 to the power of 1/4. Now remember, the rule tells you that x to the 1 over n is the same as the nth root of x, right? So you get, this can be written as the 4th root of 16. Now, what number is it that you have to raise to the power of 4 to get 16? Well, if you take a quick look at the prime factorization of 16, 2 gives 8, 2 gives 4, 2 gives 2, 2 gives 1. You can see it's 2 that you have to raise to the power of 4 to get 16. Therefore, the answer is 2. Another way you could have handled that is you could have written the 16 as 2 to the 4, right? And then you're raising to the power of 4, then you could have used the power rule. X to the m to the n equals x to the mn, right? So here we get 2 to the power of 4 times 1/4. 4 times 1/4 is, of course, 1. You get 2 to the 1, which is 2. So both methods are valid. How about this one? Now, I would like to handle this for you as a root, because remember we had the rule in the previous page that said the nth root of x to the m is equal to x to the m over n, right? And this in turn also was equal to taking the nth root first and then raising it to the power of m. So here I'm going to write this as now remember, this denominator is going to become the index. Always remember that. The denominator becomes the index, and then you can put the 16 inside. Now I can put the 5 here to the power of 5, or I can use this handy rule and put the 5 on the outside. In other words, figure out the 4th root of 16 first and then raise it to the power of 5. Now I know that that's going to be 2 to the power of 5, which is 32. All right, I think you know by now, you should be able to do it the way we did this one as well, right? So let's replace 16. So 16 to the power of 5 over 4 can be thought of as 2 to the 4. Remember, we did the prime factorization of 16. It was 2 to the 4 to the power of 5/4, right? Now notice that we can go ahead and apply the power rule and multiply the exponents. So that's 2 to the power of 4 times 5/4. Notice that the 4's cancel out, so I just get 2 to the power of 5, which once again is, of course, 32. So I'm showing you two ways of doing each of those. All right, so how about this one? Well, my preference is for you to practice these right now because you've done powers before. So notice that according to this rule, going this way, remember the index becomes the denominator. So this is the cube root of -8. Now, is that well defined? Yeah, remember the cube root of a negative number is well defined and it's going to be a negative number. So what number do we have to cube to get -8? Well, we know that if we cube 2, we get 8, right? So if we cube -2, we should get -8. So when you see this expression, cube root of -8, you have to ask yourself a question. What number do I have to cube to get -8? That's where you get your -2. How about this one? Well, before I'm going to use this definition here, I'm going to make that a positive exponent first. So we have to remember our negative exponent rule. X to the -n is 1 over x to the n. So I get 1 over 125 to the power of 4/3. So that's 1 over, now remember, we're going to use this rule, well, all three are related, right? To convert this to a radical. Remember that the denominator becomes the index. The radicand is the base. And the power of 4, I can either put it inside, or I can take care of the cube root first and then do it to the power of 4, which will be much easier. So that's going to be 1 over 5, because what's the cube root of 125? Well, let's take a look. 125, 5 goes into it 25 times, 5 goes into 25 5 times, and 5 goes into 5 once. So I know that 5 cubed gives me 125. So what is the cube root of 125? Ask the question, what number do you have to cube to get 125? 5, right? So we get 5, don't forget, to the power of 4. Now 5 to the power of 4, that's like 5 squared times 5 squared, so 25 times 25, which is 625. So there you go. There's that. How about this one here? Well, remember, the index becomes the denominator, and negative 16 goes inside, and it's just to the power of 1, so I don't need to write it. Now, what is the fourth root of negative 16? What real number can you raise to the power of 4 to get negative 16? Of course, as you know, this is not a real number. Why? Because if I take any real number and raise it to the power of 4, the result is going to be non-negative, right? Because of the even power. So there is no such real number that works here. All right, that brings us to the end of the lesson. Let's not break tradition, and let's go ahead and look at some homework problems. All right, in this problem, we're asked to write an irrational number whose digits are 4s and 2s. So obviously, since it's a multiple choice problem, we're not just going to be able to come up with any number. So we have to see which ones we can rule out. This is, of course, rational because it's terminating. This one is rational because it's repeating. This is repeating, terminating, repeating, repeating. This is one that's interesting because there is a pattern. Look, you start with 4, 2, then you go to 4, 4, 2, then you go to 3, 4s, 2. The next one would be 4, 4s, 2. So some people get confused with this. They go, wait, look, there's a pattern. So why is it irrational? Because yes, there's a pattern, but it's not a what? Repeating pattern. That's the important thing. So this actually shows you a really nice, simple way of generating an irrational number. Note that the pattern is neither repeating nor terminating. So therefore, this is an irrational number. All right, this is not a difficult problem. I just want to show you because they use a little bit of non-standard terminology in this book or notations. They use S for the set of irrational numbers. In more advanced classes, it's usually P. So just then don't get confused. I'm not going to tell you what these are. You should be able to know what these are. But I just wanted to point that out to you so you know. All right, in this problem, we're going to use prime factorization to simplify some of these radicals. As it turns out, it can be shown that one of the properties that holds for radicals is that if you have the nth root of x and multiply it by the nth root of y, you end up getting the nth root of x times y. This is definitely so if all the radicands are non-negative. So with negatives, they work as long as we have a well-defined odd index here. So let's use this property and prime factorization to, for example, simplify the cube root of negative 135. So here's the way we proceed. Let's go ahead and find the prime factorization of 135. Now we know that the sum of the digits is 9. 5 plus 3 plus 1, that's 9. So we know 3 goes into it. And I believe that's 45 times. Yeah. 3 times 40 is 120, 3 times 5 is 15, 120 and 15 gives us 135. Now I know 3 again goes into 45 15 times, and 3 goes into 15 5 times, and we have 5 goes into 5 once. So there is the prime factorization of 135. So I can take this and I can rewrite it as the cube root of negative 3 cubed times 5. Now what we'll do, first of all, notice the cube root of a negative number is going to be a negative number. So we can bring that negative out, right? So I can break this up now under one radical. I'm going to use this rule in reverse, right? So I have the nth root of a product. I want to write it as the product of the nth roots, right? So I'm going to say times the cube root of 5. So notice that I put the perfect cube part under this radical, and I kept the part that's not a perfect cube in the next radical. Now what is the cube root of 3 cubed? What number do you cube to get 3 cubed? That's almost like too simple, right? It would have to be 3. So this part here is just 3. Another way of thinking about it is, what's the cube root of 27, right? That's 3. So this part just becomes negative 3. And what are you left with? You have to bring down that negative, that cube root of 5, right? So now this is going to be the simplified version of that. So basically, you bring any perfect cubes out from under the radical in the process of simplifying these, right? I'll do one more for you and then you can try the other. So let's look at cube root of 40. Again, we're going to find the prime factorization of 40. I know 2 gives me 20, 2 gives me 10, 2 gives me 5, and 5 gives me 1, right? So I can write this as the cube root of 2 cubed times 5. Now I'm going to break it up into the cube root of the perfect cube part times the cube root of the non-perfect cube part. Now the cube root of 2 cubed, that's just 2, right? Think about it, you'll realize it. So I just get 2 times the cube root of 5. That would be the simplified version of that. All right, and you can do the other two in a very similar manner. All right, so I'll show you how to handle a couple of these and you can handle the rest. So let's say we want to solve this equation. 5 to the power of x, we've already seen similar problems, is equal to 3125, right? So what we're going to do, again, what's going to come in is prime factorization. It's going to be so useful for you. So I noticed that 4, 6, 11, it's not divisible by 3, so I'm going to divide by 5. Now I know that 3000 divided by 5 is 600, and 125 divided by 5 is 25, so I should get 625, right? And 5 again will give me 125, 5 again will give us 25, 5 again will give us 5, and finally 5 again gives us 1. Once we hit the 1, the prime factorization procedure is over. So we see that 3125 is in fact 5 to the power of 1, 2, 3, 4, 5. So I say, sorry about that interruption with my touchy screen. Okay, so we say 5 to the x equals 5 to the power of 5. So now we have two equal powers with equal bases. That implies the exponents must be equal. Remember, this is an inference, it's not a cancellation. We're using reasoning, right? So we get x equals 5, like that. All right. How about we look at part B together, D. We have the square root of negative x equals 5 radical 3. Now, how do I get this square root, this variable, out of the square root? Well, I can do that if I just square both sides. So that's what I'm going to do. So I'm just going to square both sides. So on this side, the square root of any expression squared is just itself. So I get negative x equals, on this side, I get 5 squared times the square root of 3 squared. So 25 times, what's the square root of 3 squared? You take the square root of any number and square it, you're going to get the number itself, right? What's the square root of 4 squared, for example? Well, that's 2 squared, so it's 4, right? So times 3, so I get negative x equals 75. So what is x? Multiply both sides by negative 1. Negative 75. All right. So I'm going to go ahead and erase these so I can show you maybe a couple more. All right. In this part E, we have x to the power of negative 5 over 9 equals 3, right? Now remember, I want to get x, so I'm going to raise both sides to the power of the reciprocal of negative 5 over 9. So when I multiply negative 5 over 9 by that number, I want to get 1, so that I get x to the 1, which is just x. And notice the reciprocal is negative 9/5, right? So I'm going to raise both sides to the power of negative 9/5. Okay? So now, on the left side, we just get what? We get x, right? On the right side, we get 3 to the power of negative 9 over 5. So this is going to be 1 over 3 to the power of 9 over 5, because we want to get a positive exponent. So if you remember, we can go ahead and write this as a radical. How? Well, the denominator is going to be the index, and I'm going to get 3 like that, and then to the power of 9. Now, if you recall, if I take the 5th root of 3 to the power of 9, I can break it up as the 5th root of 3 to the power of 5 times the 5th root of 3 to the power of 4, right? Now, the 5th root of 3 to the power of 5, that's just 3, right? So I get 3 times the 5th root of, now 3 to the 4, that's 81. So that's how I end up with 1 over 3 times the 5th root of 81 for that one. Now, I got into a little bit of more detail for you than they probably require. They're probably going to be happy if you just type in 3 to the power of negative 9 over 5, okay? But it's good for you to see how that would get done as well. All right, I'm going to, again, go ahead and erase so I can show you one more, okay? Part F. We have x minus 1 squared equals 3, right? So that tells me that x minus 1 is either going to be the square root of 3 or the negative square root of 3, right? Because what happens if I take square root of 3 and square it? I get 3, right? What happens if I take the negative square root of 3 and square it? That also gives me 3, correct? So now all I have to do to solve this is go ahead and add 1 to both sides. I get x equals 1 plus or minus square root of 3. That's actually two solutions. One of them is x equals 1 plus radical 3. The other one is, notice radical 3 and square root of 3, they're the same thing. The other one is x equals 1 minus square root of 3, like that. Okay, so hopefully that should help you out. Should I do one more for you? I think B you should definitely be able to handle by just writing both sides as powers of 5. Maybe I'll show you C as well, okay? So we have 25 over 9 to the power of 3x. And on this side we have 243 over 3125. All right, so this one is actually a little tricky. So notice that the idea is to try to write both sides with the same base, right? So prime factorization really helps with that, okay? Let me go ahead and erase this other one. Oh, I erased this one too. Hold on. All right, I'm just going to have to do it manually. All right, so what we're going to do is we're going to look at the prime factorization of 25, which we know is easy. That's 5 squared, right? And we know 9 is 3 squared, and that's to the power of 3x. Now for 243, 3 goes into it 81 times, 3 goes into 81 27 times, 3 goes into 27 9 times, 3 goes into 9 3 times, and 3 goes into 3 once. So it's 3 to the power of 1, 2, 3, 4, 5, okay? So I can think of this as 3 to the 5. And for 3125, we did that already, remember? 5 goes into it 625 times, 5 goes into that 125 times, 5 goes into 125 25 times, 5 goes into 25 5 times, and finally 5 goes into 5 1 time. So that's 5 to the power of 5. All right, so I have, now here I'm going to use the product, the power rule, which means multiply those powers, right? Those exponents. So I get 5 to the 6x over 3 to the 6x equals, notice that here I have 3 to the 5 over 5 to the 5. Notice that I'm getting close to something promising, because the only thing is I have these in the wrong place, right? If this was on the bottom and the 5 to the 5 were on the top, I would be in good shape. But I know because of this rule, these two rules, x to the n is 1 over x to the n, and 1 over x to the negative n equals x to the n. So I can move the 3 to the 5 down below and this one upstairs as long as I change their exponents to negative, right? So I can move the 3 to the 5 down below, it becomes 3 to the negative 5, and the 5 to the 5, I can move it to the top and it becomes 5 to the negative 5, right? So notice that I can now, let me erase these real quickly. So notice that I can now write the left side as 5/3 to the power of 6x, and I can write the right side as 5/3 to the power of negative 5, right? So finally, I'm where I want to be, correct? So that means since the two powers are the same and their bases are the same, their exponents must be the same. So we get 6x equals negative 5, divide both sides by 6, we get x equals negative 5/6. All right, a little bit tricky, I grant you that, but you will get better and better at it with practice. All right, let's go ahead and see if there's anything else we want to show you. All right, so here we have a couple of proportions with irrational numbers. So you handle them exactly the same way as if they were rational numbers. So we can cross multiply. So for part A, we get x times 1, which is x, equals square root of 7 times square root of 7. But remember, that's just square root of 7 squared, which, as you know, is just what? 7. Right? The square root of any number squared is the number itself, remember? As long as it's well defined. All right. For part B, we have 1 over x equals x over 6, right? So let's cross multiply. We get x squared equals 6. Remember the two numbers that you have to square to get 6? One of them is square root of 6. The other one is what? The negative square root of 6. So we have two solutions. Normally, we present that solution as x equals plus or minus square root of 6, like that. All right, so here's a question. Could there be a number that is both irrational and an integer? What do you think? Absolutely not, right? Because if the number is first of all, and means both conditions have to be true, right? Remember conjunctions? So if it's an integer, that means it's a rational number, right? Because you can just throw a 1 under it. And remember, rational numbers and irrational numbers, they're disjoint sets. There's no way an element can be both in the set of rational numbers and irrational numbers. So this would be impossible. All right, how about this one? You have the negative square root of 30, quantity negative square root of 36 squared and negative square root of 36 squared. Are they the same? Are they different? Well, let's see. If we take the first one, quantity negative square root of 36 squared, that's just like saying negative 1 times square root of 36, quantity negative 1 times square root of 36 squared. So negative 1 squared is just going to be 1, and square root of 36 squared is just 36. So the result is going to be what? Positive 36. But with the second one, which is negative square root of 36 squared, notice this negative is just going to carry. Because it's not being squared or anything. So the result is going to be negative 36. Remember, the square root of any number squared is the number itself, as long as we're dealing with a non-negative number n, right? So here you can see the results are different. One ends up being positive, the other ends up being negative. Be careful with those differences. They're subtle. All right, so here Jose says that the square root of negative x equals 3 has no solution since the square root of a negative number does not exist. Well, the problem with what Jose is saying is that this is the opposite of some number which we do not know. What if that number were negative, right? Like if x were negative 9, think about it. If x is negative 9, what's negative x? That's going to be 9, right? And then the square root of negative x is just going to be the square root of 9, which is 3. So you see, Jose is not necessarily right because we have an unknown under the radical. And that unknown may be negative, which means its opposite is positive, which means the square root can be perfectly, legitimately performed, and this can work. All right, so Edward asks, what if the circumference of the circle and its diameter are both integers? Then pi would have to be a rational number, right? Well, let's see what he's talking about first. First of all, you have to know the formula for the circumference of a circle. And this formula, if you recall from high school, is 2 pi r. C equals 2 pi r. So what Edward is saying is, what if we solve this equation for pi? What would we have to do? Well, we would have to divide both sides by 2r, right? Well, let me actually show you, and before we do that, let's make it easier. You know that 2 radii gives 1 diameter, right? So another version of this is c equals pi d, where d is the diameter, right? It's better to solve for pi now because the problem is dealing with diameter, not with radius. So let's go ahead and divide both sides by d. So we would end up with pi equals c over d. Now we know that pi is irrational. Okay? So is there any way for both c and d to be integers? What happens if both c and d are integers? Well, then by definition, this would be a rational number. And since it's equal to pi, that's impossible. See? So that's how you would explain it to Edward. Okay, I think that's actually a good place for us to stop. All right, I've enjoyed making these lessons for you. I hope you've learned something this term, and this is where we bring our class to a close. So hopefully we'll see you in the next class. Until then, take care of yourself and be good.